Today we're looking at seismic waves. There's more in here actually than you need, but I'll point out the things you don't need. There's a lot of this is for interest about nothing else. So seismic waves, waves produced by earthquakes. There are two kinds of seismic wave that we're interested in. There's three kinds of seismic wave, but two of them are specifically mentioned in the syllabus, P waves and S waves. Now the thing about this, really from my point of view anyway, is that we have a very clear and detailed understanding of the structure of the Earth, and yet we haven't dug in to find out what the structure of the Earth is. We have, relatively speaking, scratched the surface, and that's all. If you look at the deepest mine on the surface of the Earth, it's really a scratch in the surface, a scratch in the crust. We haven't got to the other layers of the Earth to know what they actually look like in reality. But using the way that P waves and S waves behave, knowing what kind of wave they are and where they do and don't turn up and how they turn up through the Earth, we're able to work out what the layers of the Earth are, how many layers we have, the nature of those layers, whether they're solid or liquid, the density of them, all because of the way these waves behave. So that's the remarkable thing about this, I think. You need to know about P waves, S waves, that P waves are longitudinal, S waves are transverse. And as a consequence of S waves being transverse, how we know that we have liquid at the center of the Earth. So, you should be able to label the structure of the Earth, identifying PS and L waves. L waves, they are not on the syllabus, but actually it's important to know about them generally because they're the more damaging of the three kinds of earthquake wave. So, properties of P and S waves and how we know the size and structure of the different layers. So, if we start with the picture of the Earth, this is how we understand the structure of the Earth. We have the crust here. We have the mantle here. Now there is more detail to this that I'm giving you, but this is what you need to know. You have the mantle here, you have the outer core here, and you have the inner core here. You should make yourself a copy of that diagram and label it carefully. This bit is your crust. This orange bit is your mantle. Red bit maybe. This is your outer core, and this is your inner core. So, where does the earthquake start? Well, somewhere deep in the Earth, where two tectonic plates collide. They might collide and rub against each other. That's how the plate that San Francisco sits on works. The two plates are trying to slide past each other, and eventually they do. Occasionally they do, and that causes an earthquake. And you can see that on the surface where fences have shifted relative to each other. The line of the fence has been shifted because the fence runs across the plate boundary, and one plate moves against the other, and so the fence shifts. So you have where the earthquake occurs, that is your focus of the earthquake, and directly above that, on the surface of the Earth, you have the epicenter. And we use seismometers as the devices to detect earthquakes. And later on in the course, we'll look at electromagnetic induction, and seismometers work using electromagnetic induction. And the waves that travel through the Earth as a consequence of the earthquake, they are called seismic waves. So all of these words you should come across through the lesson and by the end know what they mean. So seismic, to do with earthquake, seismometer, a device used to measure the magnitude of the earthquake. So here you have a seismometer trace, and you can see very clearly as time goes by. Initially, this is the kind of wave. You get waves here. A little later, you get another kind of wave. You can see they're different. And then here you get another kind of wave. So there's three distinct waves. Initially, P waves. Then secondary, primary, secondary, and then the L waves. So the L waves come last, but they're all produced at the same time. That's the important thing. So if we went back to here, all three waves are being produced at the same time. P waves get here, then the S waves get here, and then the L waves. So P waves, then S waves, and then the L waves. Remember, you don't actually have to know about the L waves, but the rolling motion of the L waves is what does most of the damage with an earthquake. So a table then, for 10 minutes, if it doesn't take you 10 minutes, that's fine, but I'm allowing 10 minutes for you to draw this table and fill it in. The kind of wave that P and S are, do they travel through the mantle? Do they travel through the outer core? Well, let's have a look at this. So, P waves, these are longitudinal waves, and they will travel both through liquid and through solid. So they travel through the entire Earth. And here we have, if I could make it work. I had an animation, but it's not working. So S waves then are transverse waves. Transverse waves do not travel through liquids. You might say, well, hang on here, you said that water waves are transverse waves. Water waves are often used as an example of transverse waves, but actually, if you think about the way transverse waves work, you oscillate the medium here, and the wave travels in this direction. So if you imagine two water molecules side by side, if I make this water molecule vibrate up and down, there's no reason why the water molecule next to it's going to vibrate up and down. They're not connected. So there is a certain amount of, if you like, internal friction, viscosity in water and in liquids generally, that will allow some transmission of that vibration from one molecule to the next, but it's not very effective. So transverse waves don't really travel through liquids well at all. And so that's an important property for transverse waves. They don't travel through liquids, which means they don't travel right the way through the Earth because we have liquid in there. Or rather, because they don't travel all the way through the Earth, we know there's liquid in there. So if we look at the waves as they travel through the Earth, we have got our P waves, the red ones, and when they change, when they go from one material into the next, they refract, they change speed, they change direction, and then they come out the other side, in this one's case, back into the mantle, and it refracts again. So by looking at the way the wave behaves, we know where the epicenter of the earthquake is, and we know where we detect the P waves on the other side of the Earth. We can work out how the wave has behaved as it's gone through the Earth, looking at these various positions of the P waves as they are detected on the surface, knowing where the epicenter was. And looking at the amount of refraction, we can work out the density of this layer. And we can see how this one's been refracted like this, but this one that has come deeper through the Earth has refracted differently. And this one has refracted differently. So we can work out the density of this layer and this layer and this layer by looking at the different refractions of the waves as they travel through different parts of the Earth. But if you look at the S waves, you can see a similar kind of thing. The S waves are refracted here, and the S waves are refracted here. But this wave, it doesn't make it past this layer. So we have already worked out from the behavior of the P waves that there is a layer in here that isn't out here because of the different ways being refracted. But waves, the S waves, don't make it over here. There is an earthquake shadow over here for the S waves. Now that tells us there's something different in here. That means the S waves can't travel through it. It tells us that there's liquid in there. So we know that there is a liquid core. But we know from the way the P waves behave that there is a change of density in the core because this wave and this wave are refracted differently. So we know by calculation that there is a solid inner core, a liquid outer core, and then this sort of semi-solid mantle, all from looking at the behaviors of longitudinal and transverse waves as they travel through the Earth.